Okay, so now the next one, a probability of a senior, it's supposed to be or a female. So probability of a senior or a female is equal to the probability of a senior plus the probability of a female minus the probability that you're a senior and a female. Probability of a senior is 10 out of 28. Female is still 12 out of 28. And then it's the same number for seniors and juniors, that there are 6 females in each class. So that's going to be 16 over 28, which simplifies down to 4 out of 7. Okay. What is the probability that you're a junior or a senior? So if we think about this quietly and logically for a second, the probability that you're either a junior or a senior encompasses all of the events. So if we're talking about the probability of a junior, or here, let's actually use our set notation, junior or a senior, then it's the probability of a junior plus the probability of a senior minus the probability you're a junior and a senior. Oops. Probability you're a junior is 18 out of 28. Senior is 10 out of 28. And then you can't be both a junior and a senior. And so this idea, not plus, but rather minus, the fact that your intersection between these two sets is 0, that means that this guy is mutually exclusive. So this would be a mutually, because of this, we're talking about a mutually exclusive event, which means that it's 28 out of 28. In other words, it's 100% chance that if you pick a student at random, they're going to be either a junior or a senior. Same with male or female. All right. So that's the idea of mutually exclusive versus not mutually exclusive. And the vision or the visual that I like to use with understanding the difference here mutually exclusive events are a Venn diagram where nothing intersects. There is no common ground between the two separate events. This is event A and this is event B. Whereas not mutually exclusive would be events that do overlap, where they share a common ground. You can be both a king and a heart. You can be both a junior and a male. So that's the visual that I like to have in mind for exclusive versus not mutually exclusive versus not mutually exclusive, is it's a Venn diagram. Now, independent versus dependent. I know we talked about these with our L to J's because it popped up quite a bit, even though it was at random, which skills we were going to have. This one popped up quite a bit. Independent versus dependent is this idea of one event affecting the outcome and the sample space of your next event. If you're pulling from a bag of marbles and you've pulled one marble out and you're finding the probability of something with the second marble, there's one less marble in the bag after you've pulled one out. So those are dependent events. The event of the second marble being pulled is relying on what happened with the first marble. Versus if you're talking about the probability of like this, a fair coin being tossed 3 times, all 3 tosses are heads. What's the probability that the 4th toss will be heads? Since coins don't care what happened before, and coins don't care what happened after, each coin flip is its own independent event. I wrote something down. So the probability is still what it would have been if we were talking about what's the probability that the 6th coin flip will be a heads, or what's the probability that the 20th coin flip will be tails. It's still going to be the same one every single time because they are independent events. Now, if you want to know what's the probability of all 4 coin tosses being heads, then that would be a different story. We're not saying like what's the probability of all 4 of them being heads. We're asking what's the probability that the 4th one will be heads, and that's just its own independent event. Okay, the multiplication rule, I'm going to give you the definition and then we're going to use it, as opposed to with the addition rule, we saw it in action and then we defined it. We're now going to define it first and then see it in action. So the multiplication rule, just like the addition rule, is exactly as it sounds. We're going to be multiplying our probabilities together as opposed to adding our probabilities together. But it does change depending on whether it's an independent or a dependent event. But if you think about it, not really. Okay, so independent events are events where the outcome of one event does not affect the outcome of the second event. The difference with the multiplication rule and the addition rule is that with the addition rule, we're looking for the word or. With the multiplication rule, we're looking for the word and. So actually, let's go up here and write down and. And remember with set notation that the notation for and is the bridge between the two. In set A and in set B, there's going to be something that they share, and that's like a bridge connecting the two things that they share. So the probability of A and B, if they are independent events, you just take the probability of A and you multiply it by the probability of B. So if we're talking about multiple coin flips in a row and we're saying, what's the probability that all 3 of them are heads? You would say, well, it's 1/2 times 1/2 times 1/2, which would be a total of 1/8. Because all of those are independent events. With dependent events, the outcome of one event does affect the outcome of the other. So this one does not, and this one does. And it's still going to be multiplication. We're talking about the probability of A and B. And if A and B are depending on each other, it's still going to be the probability of A. And then it's going to be multiplied by the probability of, and you'll see this in notation, it's the probability of B. And then you've got this line, just a straight line that comes down, and it means given, or such that A has occurred. So probability of A times the probability of B given A is how you kind of say it when you see this shorthand notation. And it's the idea that if you're pulling from a bag of marbles, if you pull one marble out, if you have 5 marbles and 2 of them are green and 3 of them are yellow. You've pulled one marble out and one color is less and the whole bag is less. So if we're talking about probability that you've picked 2 green marbles, then it's going to be a probability of 2 out of 5 for your first probability. But for the second probability, you've already picked out one of those green marbles. So now you only have 4 marbles, and now there's only one of them that is green. So then your numbers change given that the first probability has already happened. So then your probability of B given A would be 1 out of 4. And it is this idea, you'll see as we go in, this idea of factorials happening. You'll see us going down by 1, especially because normally we're just talking about pulling one thing away from whatever dependent event we're talking about. So that's a definition of independent versus dependent. And that's how you do the multiplication rule based off of whether it's independent or dependent. So let's put it into practice. What is the probability of a mother giving birth to 2 boys in a row? Is this independent or is this dependent? Does the fact that she had a boy the first time have a real play on whether she'll have a boy the second time? No, those are 2 dependent events. So the probability of her having a boy the first time is 1/2. And then the probability of her having a boy the second time is still 1/2. And we just have to, because it says probability of first boy and second boy. It doesn't actually say the word and, but it's implied in this situation. So sometimes you won't always see that word, and you have to make sure that you're reading into the subtext of the conversation. It's not that she has 1 boy out of 2, so 1 or, never mind, that thought process doesn't work. But looking at it, it would be an and situation. You multiply these together and you get a 4th. 5 boys in a row? Well, you just do 1/2 times 1/2 times 1/2 times 1/2 times 1/2, and that's equal to 1/32. And there you have it. Okay, so returning to an earlier problem that we talked in our first set of notes, so our notes that we talked about last class, talking about probability that if you're dealt 3 cards from a deck randomly, the probability that all of them are queens. So that the first, second, and third card are all queens. Now, if you pull from a deck of cards, you're pulling from the same sample set. And if you pull one out, if you're talking about pulling a second one, then this is a dependent event, because now we started with 52 cards and now we have 51 cards. And if we start with 4 queens and we want to talk about, well, what's the probability that the first one was a queen, the second one was a queen, and the third one was a queen, we're also losing queens as we go down. So it's still multiplication, but we've got a possibility of 4 out of 52 queens. And then after we've pulled out one of those queens, we only have 3 left over 52 times, and then we still have 2 queens left over 52. And that would be, I already did the math, 24 over 132,600. Simplifying that down, we get 1 over 5,525, which is the same number that we got above. It's just done in a different way. Instead of choosing our combinations in order to figure out the possible occurrences of this happening, we've used it as this idea of a dependent event of things losing their number as we go down. Okay, so let's practice this a little bit more. Determine that the probability of there being 0 queens.